In this video, we'll talk about Simpson's rule, which is another method for finding integrals numerically that's more complicated but has better results. So Simpson's rule comes about when we try to think, well, can I do better than straight lines between points? So you can think of the trapezoid rule as saying, let me take these two endpoints that I have, and just draw the straight line between them and use that to approximate my curve between those 2 points. What if I want to do more than just straight lines? Simpson's rule thinks about what if I want to do quadratics instead? So trapezoid rule said, let's take the best fit line to this curve, which is between 2 points to draw the straight line between them, and use that to approximate the curve. Well, Simpson's rule says, what if I do parabolas instead? Now, to do parabolas, I need to take 3 points, not just 2. So I take a set of 3 points, and then want to draw the parabola that goes through those 3 points, and use that to approximate my function in order to find these areas. And then that's going to become the shape that I sort of tile along this curve to give me an approximation to the area under the entire thing. And you can sort of see what that's doing in this picture up here. So the idea is that through these points, P0, P1, and P2, I have this light blue arc here. And that right there is the parabola that goes through those 3 points. I'm then going to approximate the area under the curve in here by the area under that parabola. And then I continue this for every set of 3 points that I see. So I see P0, P1, P2, that gives me a parabola there. And then I have P2, P3, and P4. I find the best parabola there. I find P4, P5, and P6, and I have the best parabola there. Basically, for every triplet that I see, I draw the parabola between them, and I use that area to approximate the area under my curve. So instead of having a rectangle, which you could do rectangles as well, but for this setup, we're using parabolas to approximate the areas and not rectangles. So what does this formula here look like? Well, the issue really comes down to, how do I find the area under a parabola that I know goes through 3 points? So if I were to have 3 points here that I know are at, for instance, we'll say this is y0 and negative delta x. This is at y1 and 0, and this is at y2 and delta x. Right, we're going to assume we have evenly spaced rectangles here. And so on one side you go minus delta, the other side you go plus delta x. I want to figure out what the area of this region is, because that's going to form the basis for how I figure out this formula. There's a derivation for the formula for this area in the book. The main idea is it's a quadratic, so it's going to be of the form ax squared plus bx plus c. You can then use undetermined coefficients like we did for partial fractions to figure out what a, b, and c have to be based on y0, y1, and y2, and then integrate. And what you will come to is that this area is delta x over 3, y0 plus 4y1 plus y2. So the way you want to think about this is for each parabola, the area is delta x over 3 times the left plus 4 times the middle plus the right. This will be the same idea like we have for trapezoid rule, where I had to sort of stagger these on top of each other. That's what I'm going to get for this setup here. So we're going to use capital S sub n for the Simpson's rule approximations. So for this one, we need to assume that n is even. Otherwise, my parabolas don't work out correctly. So then what do I get for this? Well, then Sn should be, what's the area of the first parabola? Well, it's going to be a delta x over 3 times a y0 for the first y-coordinate, plus 4 copies of y1 plus a y2, since that's left, middle, and right for the first arc. Then I want to add in the second one. And the second one will stretch from 2 to 4, because that's the next 3 points that I see. Plus a delta x over 3 times a y2 plus 4 y3s plus a y4. And this process continues. I get from 4 to 6, a delta x over 3, a y4 plus 4 y5s plus a y6. And this continues to the last term, where I get a delta x over 3, a yn minus 2, a 4 yn minus 1, and a yn. Now if I want to make this look nice, we can see how these ones will combine. And what you'll see is all the odd ones come in with a 4 in front of them. The even ones all appear twice, once as a left and once as a right, again except the first and last terms. They come in only once. So the formula that I should get for this is the following. Sn is going to be delta x over 3. y0 comes in once, y1 is in 4 times, y2 is in twice, y3 is in 4 times, y4 is in twice, and so on, up until I get 2yn minus 2's, because that will appear with the one before it as well, 4yn minus 1's, and a single yn. And these y values are the function values at our endpoints that we had before. They are endpoints of n plus 1 equally divided points, with a delta x being still b minus a over n like it always is. That's the formula you need for Simpson's rule. Basically, I always remember it as 1, and then 4, 2, 4, 2, 4, 2, 4, 2, alternating throughout the whole thing, and then a 1 again at the end. Let's apply this for here. Compute S6 for the function y equals x squared on 0 to 6. And let's see what we get for this. So my delta x again is 1, which is how these problems have been set up. How do I get S6? Well, I get S6 by taking delta x over 3, and then I have 7 points, so I'll get a y0, I'll get 4 y1s, 2 y2s, 4 y3s, 2 y4s, 4 y5s, and a y6. There's my 7 points. Now I just plug them all in. So I'll get a delta x over 3, y0 is 0, y1 is 1, it's 1 squared, 2 squared is 4, so that gives me an 8, 3 squared is 9, it's a 36, 4 squared is 16, so a 32, 5 squared is 25, so 100, and then 6 squared is 36 again. This delta x is a 1 out front, and I add all this up, comes out to a 216 over 3, which is a 72. And if you look, this integral is actually exactly correct. Why is that? Well, it's because my function was a parabola, and I was fitting to it with parabolas, meaning I was getting every single area exactly correct because I was using parabolas for the approximating shape. If I had used lines, this would not be exactly correct. But if I had done straight lines on a straight line function, then that would be correct. So these things can be right if the function's simple enough, but for more complicated functions that you're going to be using, these won't be exactly correct, but they will be accurate. And we'll see in the next video what we mean by these things being accurate or being good approximations when we look at error bounds on these functions. But here, this is the idea of Simpson's rule. This is how you use Simpson's rule to calculate and approximate numerical integrals in these sorts of problems.